This is going to be the second half of Module 15, which is on electrical circuits. And we finished last time by talking about circuits that are in series and those that are in parallel. So just by way of review, a series circuit is one in which the resistors are lined in the circuit so that in order for the current to flow from one end of the battery to the other end, the current must flow through all of the resistors. So if one resistor breaks, then the current will stop flowing. And then we contrasted that to a circuit in which the resistors were in parallel. And in parallel, the current has some choices that it can make about the way that it flows. So this would be an example of a parallel circuit. So here, in flowing from one side of the circuit to the other, the current doesn't need to flow through every resistor. It has some choices that it can make, and therefore that's called a parallel circuit, where the resistors are in parallel with each other. So we have said that the electric potential V is equal to I times R. I is current, R is resistance. And we'll do a little experiment when we get together during the last class period. But if we put the resistance, if we think about the resistance of two resistors in parallel. So if you have two resistors in parallel, like the example that I just drew, the resistance is lower than the resistance of just one of the resistors. So two resistors in a circuit, if they are arranged in parallel, the resistance of those two resistors will be lower than the resistance of just one of those resistors. So if you have a single resistor with current flowing through it, two resistors in parallel allow for more current to flow through a single resistance. So if we think about this in terms of the mathematics involved. Okay, so so you're going to have a certain amount, the battery or the wall source is going to provide a certain electric potential. So this is going to stay the same. So if it is true, as we just said, that if you have resistors arranged in parallel, then that's going to result in a lower resistance. So if you lower the resistance, so if you lower R, then I must increase. The current must increase if you lower R in order to keep the electric potential the same. Okay, so resistors arranged in parallel result in a lower resistance for the two resistors than if you just had one. Now, the situation is different if they are arranged in series. So again, if this is a circuit, and we have these arranged in series. So again, in order for current to flow from one end of the battery to the other, it needs to flow through all the resistors. So if one of those resistors break, then the the current will stop flowing. So for this one, and we use the term R effective, so it just means that basically the resistance that you observe is going to be equal to the resistance of 1 plus the resistance of 2 plus the resistance of 3, and if there's more than that, it's just the sum of all the resistors. So in a series, in a circuit where the resistors are arranged in a series, you could replace all of these resistors with a single one in the circuit that was equal to the sum of these three. So we could take this circuit and we could I don't need that one there. Let's do that again. So we could take this circuit and we could replace these three resistors with one resistor whose resistance is equal to R1 plus R2 plus R3. Now, if we look at them when they are hooked up in parallel, so hooked up in parallel, we said that the effective resistance would be lower than the resistance of the individual resistors. So again, if we look at the total current, if you have a total current that is I, then some of the current is going to flow through R1. We'll call this R1. Some of it will flow through R2, and some of it is going to flow through R3. So if I1 plus I2 plus I3 is equal to I. So you have a certain amount of current that is flowing through here. So that current's going to flow like this. Well, that current can flow across here. It can flow across here. It can flow across here. So some of that current is going to flow through each of these resistors. And so that I1 plus I1 plus I2 plus I3 is going to equal to I, because the current that leaves this side of the battery has to be equal to the current that enters on this side of the battery, the current that reaches the other end. So I can take you through the mathematics of this. Don't worry too much about the derivation. So in other words, we could say that I1 is equal to V divided by R1, and we could say that I2 is equal to V divided by R2. And remember, the B is not going to change because you have a certain amount of electric potential either coming from the battery or coming from the wall. And I3 would be equal to V divided by R3. So then what we could say then is that I is equal to V over R1 plus V over R2 plus V over R3. And again, remember that the I means that this I means that whatever current leaves here has to arrive at this end. So that current's going to stay constant. So then we could rearrange that all, and we could say that I is equal to V times 1 over R1 plus 1 over R2 plus 1 over R3. So then we can then say that 1 over R, the effective R, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So again, then we ultimately get that I is equal to V divided by R effective. Okay, so the bottom line about what you need to remember from all that derivation is that 1 over the effective resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And if that's confusing, don't worry about it. We'll look through a problem that should help to explain it. Okay, so let's look at example 15.3 in your book. So in that example, we have a circuit that looks like this. I drew this line really long. It doesn't need to be that long. Okay, so there's our circuit, and this resistor is 12 ohms, and this resistor is 15 ohms. So then these are arranged in series, because in order for the current to flow from one side of the battery to the other, it needs to go through both of the resistors. So it's arranged in series. So that tells us that R effective, the effective resistance, is equal to R1 plus R2. So this would be 15 ohms plus 12 ohms, or 27 ohms would be the effective resistance. So that what that means is that in our circuit we could replace those two resistors with a single resistor that has a resistance of 27 ohms. So that circuit could be replaced with a circuit with just one resistor that is 27 ohms. Okay, so that's when they are in series. Okay, then what if we have one that looks like this? Okay, so now this resistor is 15 ohms, and this one in here is 12. Okay, and these are arranged in parallel because the current can leave when it leaves the positive, which would be this one. It doesn't have to flow through both resistors to get back to the other side. It has a choice to make. It can either go through this one or it can go through this one. So they are arranged in parallel because the current has a choice about which path to take. Okay, so then we know that 1 over R effective is equal to 1 over R1 plus 1 over R2. Okay, so this would be equal to 1 over 12 ohms plus 1 over 15 ohms. That's equal to 1 over R effective. So what we would get then is, this is going to be 1 over, it's going to be 0.083 ohms plus 0.067 ohms. And so this will be equal to 1 over 0.150 ohms. Okay, and that's going to be 1 over R effective. So if we go ahead and divide that 1 divided by 0.150, that will give us the effective resistance. So that an R effective is equal to 6.67 ohms. If we look at significant figures here, so here when you're adding these together, because it goes 3 places from the decimal place, you have to go out 3 places for the decimal place here. So that gives us the 0.150. And then that also, when we're dividing, then 1 divided by that, we're going to have 3 significant figures. So it would be 6.67. So again, what that means is that you could, this circuit, so the effective resistance of these two resistors, as you see, is lower than each individual resistor. And so again, we could draw this circuit and we could replace those two resistors with just a single resistor that was 6.67 ohms. Okay, so that is when they are arranged in parallel. Okay, so let's do on your own 15.5. And you can see there that in the drawing that is given, there are 3 resistors, and those resistors are arranged in parallel because in order to get from one side of the battery to the other, there are choices that can be made. It doesn't have to flow through each one. So then in order to figure out the resistance, we would say that 1 over R effective is equal to 1 over 111 ohms. These numbers are what's given to you, plus 1 over 222 ohms, plus 1 over 333 ohms. Okay, so then this would be 0.00901. We need 3 significant figures, plus 0.00450 plus 0.00300. Okay, so we've taken each of these, we need 3 significant figures, and these would all be in ohms. But now when we're adding, we need to go out 5 places from the decimal place. So this would be that 1 over R effective is equal to 1 over 0.01651 ohms. And so the effective resistance, so this has 4 significant figures now when we divide. So R effective is going to be equal to 60.57 ohms. Okay, so the resistance for that parallel circuit is going to be 60.57. And again, you can see that that is less than the resistance of any of the individual resistors. Okay, then on your own 5.6 or 15.6, now we have resistors that are arranged in series, and those resistors are 111 ohms plus 222 ohms plus 333 ohms, and because they are in series, our effective is just going to be the sum of those. So that is going to be 666 ohms. Probably as much or more than other topics that we have studied in physics. This is a topic that's easier to see some of the practical applications. So when a house is being wired for electricity, the electrician needs to make sure that the right number of resistors are on each circuit. So when we draw these circuits, and we draw in these resistors, you can really think of each of these resistors as being representing like individual devices or individual outlets in a house. So this might be a toaster, this might be a hairdryer, this might be a light bulb. So when a house is being wired for electricity, the electrician needs to make sure that there's the right number of resistors on each circuit. So each of these devices is going to affect how much current flows through the circuit. And if you get too much current flowing through a circuit, so more current flowing through a circuit, remember these circuits, the resistors are going to generate heat. So more circuits equals more heat. And if you get too much current and therefore too much heat, it could lead to a fire. So you have to limit the current that is available in a circuit. And there are two ways that electricians can do that. One we don't, in newer homes, we're not using these anymore, but one way is by using a fuse. So a fuse is a thin conductor. That is sensitive to heat. And if too much heat flows through, if too much current flows through, then the conductor gets hot enough that the conductor breaks, and then that's like having an open switch and current can't flow, and we say then that you have blown a fuse. So here is what, if we had a circuit that used fuses, so I'll draw a parallel circuit. So let's say that we have one of these lines shorter than the other. So these are the resistors within this circuit, and there is a fuse here. So this fuse has this conductor here. So if the current flowing through this becomes too great, then what happens is that fuse gets hot enough, the heat that is generated is enough to, so this would be the same, we'd still have our resistors in there, but now that conductor that was in the middle of that fuse breaks, and therefore the current can no longer flow through this circuit because that connection is not there. So the metal in the fuse is broken, and so that's if that's one way that that is used to deal with too much current flowing through an electrical circuit, is the fuse will blow, so then the whole thing will shut down, and therefore you mitigate the chance of fire. And the only way you can get this to go again is then to replace the fuse. Okay, the other way that is used to control the heat is with circuit breakers. And most newer homes, or even in older homes, many, if they've been rewired, they're going to be now with circuit breakers. And what a circuit breaker is it is a switch that bends when it gets too hot. So if you have too much current flowing through a circuit, it's going to heat up and it's going to bend the circuit breaker. And when it gets too hot, then that's like opening this. When it bends, that's like opening the switch. So with an open switch, then electricity can't flow. So both a fuse and a circuit breaker are ways to prevent the circuit from drawing too much current and getting too hot. And then you have to either replace the fuse or to the circuit breaker, you can just reset it by flipping the switch back again. Okay, so let's look at some ways that we can apply this. And we'll look first at example 15.4. And example 15.4 tells us that we have an electrician has fuses that are rated at 5 amps, 10 amps, 15 amps, and 20 amps. And this electrician needs to decide which fuse should be placed in a circuit. Okay, so here's our circuit. This is drawn in your book. Okay, so the voltage is 120 volts, and the fuse is going to be placed right here. And we want to know which amperage should that fuse have. Okay, so that means that we need to figure out the current that can safely flow through this circuit. Okay, so we know that I, or V, equals I times R. Okay, so we know V was given at 120. If we can figure out the resistance, then we'll be able to figure out the current that will flow through this with these 3 resistors. Okay, so the first thing that you should notice is that these circuits are, I'm sorry, I might have drawn the wrong picture, did I? Actually, I think I'm sorry, I jumped ahead and I'm doing on your own 15.7, and that's okay. We'll go ahead and do that one. And then it illustrates the same thing. Okay, so this is our situation, and we are given, so that's 120 volts, and our resistors are 8.0 ohms and 5.0 ohms. Okay, so then we want to know which of these fuses should the electrician use. So we need to figure out resistance. Okay, so these resistors are arranged in series because in order to flow from one side to the other, it has to go through both of them. So that means that R is going to be equal to just the sum of the resistors. So it's going to be 8.0 ohms plus 5.0 ohms. So that will be equal to 13.0 ohms. Now, the significant figures you would, since you're adding, you're going to take it out to the tenths place because each of these values that we added went out to the tenths place. Okay, then if V equals I times R, then V divided by R was equal to I. So 120 volts divided by the resistance of 13.0 ohms is equal to 9.2. So we can have two significant figures now because of the 120. So 9.2 volts over ohms, which you learned last week, is an amp. So it would be 9.2 amps. So then what that tells us then is that given the choice of these four fuses, the electrician wants to choose the one that is closest to 9.2, closest but larger than 9.2 amps. So he would choose the 10 amp fuse. If he chose the 5, there would be too much, current would never flow because the 9.2 amps would blow that fuse every time. And if you put in a larger one, that is it could allow too much current to flow, and that could overheat and cause a fire. So you want to choose a fuse that is larger than the current but close to the current. Okay, so that is on your own 15.7. Let's go ahead and do on your own 15.8. And I will go ahead and draw this. I'll need to erase it so you can look at it in your book as well. So in this circuit, it's going to look like this. Okay, and again, we have 120 volts over here. And this one is 12 ohms. This one is 25 ohms. And this resistor is 15 ohms. Okay, so the first thing you have to ask yourself is this parallel or is it series? And so in order for the current to flow from the positive end to the negative end, it doesn't need to flow through every resistor. There are some choices that are available, and therefore this is arranged in parallel. Okay, so that tells us then that R effective, or 1 over R effective, is equal to 1 over 12 plus 1 over 25 plus 1 over 15, and all this would be in ohms. Okay, so this would be 1 over 0.083 plus 1 over 0.067. I put those in the wrong order. 1 over 0.040 and 1 over 0.067. Again, it's going to be ohms, and that will be equal R effective. So R effective is going to be equal to 1 over, we add these together, you're going to get 1 over 0.1 And again, we're going out 3 places beyond the decimal. We're going to the thousandths place, tenth, hundredths, thousandths, because we're adding. But then when we divide, we'll still have 3 significant figures. So our effective is equal to 5.26 ohms. Okay, so we are asked what is the current and what is the power. Okay, so current, we know that V is equal to I times R. So V divided by R is going to be equal to I. The V we were given as 120 volts. The resistance we just calculated as 5.26 ohms. So that will give us, with 2 significant figures because of the 120, you're going to get 23 volts over ohms, which is an amp. So I, the current, is equal to 23 amps. Okay, then power, we learned last week, there's 2 equations that we can use for power. We can say that power is equal to I times V, or power is equal to I squared R. So it doesn't matter which one you use. It's easier if you don't want to. It's easier to just to deal with 2 variables, in my opinion. So we'll put the I as the 23 amps, and we will put the V as 120 volts, and an amp times a volt is equal to a watt. So this comes out to 2,760 volt amps. With 2 significant figures, you would write this as 2,800 volt amps is a watt. So power is equal to 2,800, or you could do 2.0 times 10 cubed watts. Okay, so that is on your own 15.8. Okay, now, so those are the ones that we've done so far are more simple circuits, but they can get more complicated. So I want to go ahead and work through example 15.5. So let's draw this circuit. Okay, and then the battery is a 1.5 volt battery, and this resistor is 25 ohms. This one is 15. This one is 35. And this one is 11. Okay, so the first thing we have to do, so we're going to start at the positive end of the battery, and you're going to move to the negative. And you're going to figure out which of these resistors are in parallel and which are in series. Okay, so if we start here at the positive end, and we start moving toward the negative. Well, it doesn't ever. It's going to have to go through this 25 ohm. Okay, so that tells us that one is in series. So the 25 ohm one, since it has to go through it, there are no choices there. That one would be in series. Then when it gets up here, it can either go through the 11 or it can go through the 15. So those are in parallel. So the 11 and the 15 are in parallel. And then again, whichever, it doesn't matter if it goes this way or it goes this way. In order to get back down here to the negative side, it has to go through the 35. So the 35 is also in series. Okay, so it has to go through the 25 and the 35, and then it has choices to be made with in terms of the other. So what we have to, so if we were to want, if we would need to figure out the power or the current on this, we would first need to figure out the effective resistance for that. So these two, because they are in series, we know that R effective is just R1 plus R2. So it would be 25 plus 35, which is 60. And we need, because we're adding, we just need to go out to the ones place. So 60 is going to be okay there. And then for the parallel, the effective resistance is going to equal 1 over 11 plus 1 over 15. So it's going to be equal to 0.091 plus 0.067. So it's going to be 1 over 0.158. Again, to get two significant figures here, we had to go out to the thousandths place, so we'll go out to the thousandths place there. So R effective is 1 divided by 0.158. So with three significant figures, R effective is equal to 6.33 ohms. Okay, so then the total is going to be the resistors that are in parallel, in series, plus the resistors that are in parallel. So it's going to be 60 plus 6.33. So 60 plus 6.33. So here again, we're adding, so we can go out to the whole number. So it's going to, it's 66.33, but we can just go out to the whole number, so it's going to be 66 ohms. Okay, so then if we were to figure out if we want to know the power, so power is equal to IV. So we need to first figure out what I is. So V is equal to I times R. We just calculated R and we were given V. So V divided by R equals I. V we were given as 1.5 volts. We calculated the resistance as 66 ohms. So I is equal to 0.023 volts over ohms, which is an amp. And we can have two significant figures there, so that gives us our two significant figures. Okay, now we can take that, and using that information, we can calculate the power. So power is I times V. We just calculated I to be 0.023 amps. We were given the voltage as 1.5 volts. So 0.023 amps times 1.5 volts is 0 with two significant figures, 0.35 amp volts, which is a watt. So the power is 0.035 watts. Okay, let's do on your own 15.9 and 15.10, and we will then be finished. Go back to, okay, so on your own 15.9. So we are told in this problem that we have three fuses. One is a 1 amp, a 3 amp, and a 5 amp. And here is the circuit that we have. Okay, so this is a 9-volt battery, and the resistors, this one is 1.0 ohms. This one is 2.0 ohms, and the one in the middle is 3.0 ohms. Okay, so again, we're going to look at the power, and the power is going to flow from the positive end of this battery. It's going to flow from the positive around to the negative. So in order to do that, when it gets here, it's going to have a choice. It can either go through the 3 or it can go through the 2. So that choice means that those two are in parallel. So the 3.0 and the 2.0. But it doesn't matter whether it goes through the 3 or the 2. It must go through the 1, so that one is in series. Okay, so R in series, it's just the sum, and since there's only one, the R effective would be 1 ohm for that one. But then let's look at the parallel one. So the parallel one is going to be so 1 over R effective is going to equal to 1 over 3.0 plus 1 over 2.0, and these are in ohms. So it's going to be 1 over 0.33 plus 1 over 0.50. So this is going to be 1 over 0.83 is going to equal R effective. So R effective, so that one is going to equal 1.83 ohms. And then the other one that we saw, the one that was in series, is 1.0. So we'll just add those two together. We're adding, so we can go out to the tenths place. So this would mean that the total is 2.2 ohms. Okay, so then in order to figure out which of these fuses, these are currents. So how high can our current be, or what current is flowing through the system so that we know which fuse to use. So B equals I times R. V divided by R equals I. Okay, V we are given as it was 9 volts. And the R we calculated as 2.2 ohms. And so I, with two significant figures, I is going to be equal to 4.1 volts over ohms, which is equal to 4.1 amps. So then if we look at our fuses, these two would not be large enough because a 4.1 amps of current would blow those every time. So we would this circuit would need to use a 5 amp fuse. Okay, one more we'll do on your own 15.10. And this one, I'm going to ask you to go ahead and refer to the book because the circuit that is drawn is pretty complicated. But the question that we're answering is how much power is used for the following circuit. So we're on your own 15.10, which is on page 514. So again, when we start, we're going to start at the positive, and we're going to go through, follow the current over to the negative side. Well, the first thing that you see is that it's going to first encounter a 22 and a 29 ohm, where it has a choice of which way to go. So those two are in parallel. Then it's going to, once it's through those, then the current's going to converge in one circuit again, one wire again, and then it's going to encounter a 13 and a 15 where it has a choice. So those two are in parallel. Then the wire comes together again, and it's going to encounter a 39 and a 31. And then it comes together again and ends at the negative side of the battery. So this is 120 volts, and these are in parallel. These are in parallel, and these are in parallel. But then, because that circuit comes back together again, we're going to add those. So this first one would be 1 over 22 plus 1 over 29. So this would be, and then this is going to be 1 over 29. So this would be 1 over, let's go ahead and do this one first. So this would be 1 over 0.045 plus 1 over 0.034. So that will be equal to 1 over 0.079 ohms. So this one is equal to 13 ohms. Okay, so the first set of resistors is 13 ohms. Okay, then we can do the 13 and the 15. Those also are in parallel. So it's going to be 1 over 13 plus 1 over 15. So it's going to be 1 over 0.077 plus 1 over 0.067. And that's 1 over 0.144, or with 3 significant figures, 6.94 ohms. Okay, so that's the 13 and the 15. Let me separate. So these are the ones we have so far. We have that one, and we have this one. And then the last 3 were 39 and 31. So 1 over 39 plus 1 over 31. And then to get that's equal 1 over R effective. So then you have to take 1 over that to get R effective. So it's going to be 1 over 0.026 plus 1 over 0.032 is equal to R effective. So this is 1 over 0.058, which is equal to, with 2 significant figures, 17 ohms. Okay, so now we're going to treat those 3 as being in series, because whichever path it chooses, the wire comes back together, and then when it meets the next resistor, it's going to have a choice. Then it comes back together, and then when it meets the next one, it's going to have a choice. So we have a 13, a 6.94, and a 17. So the resistance is going to be 13 ohms plus 6.94 ohms plus 17. Now let me say about significant figures. We're adding here, so we can just go out to the ones place. So when I add those together, I will get, going just out to the ones place, you're going to get 37 ohms. Okay, so then we were asked, what is the power? Well, to get the power, we got to get current. V equals I times R. V divided by R equals I. The V we were given as 120 volts. And the resistance is 37 ohms. So I, with 2 significant figures, is going to be 3.2 volts over ohms, or 3.2 amps. Okay, now, and then we're still not there because we wanted to know what power is. Power is I times V. So power is I that we just calculated, 3.2 amps, times the voltage which we were given, which is 120 volts. So P is equal to, it's going to come out to 384. An amp times a volt is a watt, but we can have just 2 significant figures. So the power would be equal to 380 watts. And that's our answer, because they asked us, we were asked for power. Okay, so we are going to stop there. That is the end of the information in Module 15. In a separate video, all of the solutions to the practice problems for Module 15 will be recorded.